Imagine pointing a telescope at a quiet patch of sky and finding what looks, at first, like almost nothing. Not a spiral galaxy filling the frame, not a giant red star swelling in the darkness, not a glowing nebula shaped like a storm, just a faint point of light, so distant that its photons began their journey when the universe was much younger, and so bright that the galaxy around it is almost erased by its own core. That point is TON 618, and hidden inside it is one of the largest black holes astronomers have ever measured. Not a black hole that is simply bigger than the Sun, not one that is only bigger than the center of the Milky Way. A monster measured in tens of billions of solar masses, so large that even the word supermassive begins to feel too small. But the strange part is not just that TON 618 is huge. The strange part is that something this huge should not feel easy to explain. A black hole grows by feeding. It needs gas, stars, mergers, time, and a galaxy around it that can keep throwing matter inward. Yet, TON 618 is so extreme that it forces a deeper question. How does nature build an object so massive without tearing apart the story we thought we understood? Before we begin, subscribe to the channel if you enjoy calm journeys through the universe. Leave a like if you want more long space documentaries like this, and write a comment telling us where you are watching from and what time it is for you right now. It is always strange to remember that, while we are looking at the same universe, we are all watching it from different places on Earth. Tonight, you are watching the Space for Sleep channel, talking about TON 618 is big enough to break reality. And to understand why this object feels so impossible, we have to begin with a very important correction. TON 618 is not only a black hole. TON 618 is the name of a quasar, a blazing active galaxy core powered by a black hole hidden inside it. If the black hole is the engine, then the quasar is the fire pouring out around that engine. The black hole itself gives off no light from within its event horizon. Nothing that crosses that boundary returns, but the material falling toward it can become one of the brightest things in the universe. Gas spirals inward, dust is crushed and heated, magnetic fields twist through plasma, matter rubs against matter at unbelievable speeds, and before some of it disappears, it releases energy across space as light, heat, ultraviolet radiation, X-rays, and sometimes enormous jets. A quasar is not bright because the black hole shines. It is bright because the black hole is feeding violently enough to turn its surroundings into a cosmic furnace. That is what makes TON 618 so strange to look at from Earth. In ordinary images, it can resemble a star-like dot. It does not show itself as a giant hole in the sky. It does not appear with a dramatic edge or a visible mouth. The reason is distance. Its light has crossed billions of years of expanding space before reaching us. By the time it arrives, the entire quasar is reduced to a small bright point, one that hides an object larger than almost anything the human mind naturally knows how to picture. So the first terrifying lesson is simple. The universe can hide impossible scale inside something that looks small. A mountain looks huge because you stand near it. The moon looks manageable because it is a familiar disk in the night sky. Saturn looks tiny through the naked eye because distance has compressed it into a point. TON 618 pushes that effect to an extreme. The object is not small. We are simply seeing it from so far away that its size has been folded into light. To begin measuring it, astronomers do not fly there. They do not place a probe in orbit around the black hole. They study the spectrum of the quasar. They break its light apart and search for the fingerprints of elements and moving gas. In the light from quasars, some emission lines are broadened, which means the gas creating them is moving at enormous speeds. The faster that gas moves, and the farther it is from the center, the more gravity must be controlling it. From those clues, scientists estimate the mass of the black hole. The exact number is difficult, and it should be treated carefully. TON 618 is very far away. We are not watching stars complete neat orbits around it, the way astronomers can study stars near Sagittarius A, the black hole in the center of the Milky Way. Instead, TON 618 is measured through quasar physics, luminosity, emission lines, and models of gas moving near an active nucleus. That means the number is not a casual fact carved into stone. It is an estimate built from light, equations, and assumptions. But even with that caution, the scale remains enormous. NASA describes TON 618 as containing more than 60 billion solar masses. That means the black hole is not 60 billion kilometers across. It means its mass is more than 60 billion times the mass of the Sun. Mass is the amount of matter and energy pulling through gravity. The Sun already contains more than 99% of all the mass in our solar system. TON 618 is not a little heavier than the Sun. It is tens of billions of suns compressed into a region defined by an event horizon. That number breaks ordinary comparison very quickly. Earth has one Earth mass. Jupiter is about 318 Earth masses. The Sun is about 330,000 Earth masses. Sagittarius A, at the center of the Milky Way, is about 4 million solar masses. That is already enormous. If Sagittarius A replaced the Sun, its event horizon would fit inside the orbit of Mercury, while its gravity would completely reshape the solar system. Then there is M87, the famous black hole imaged by the Event Horizon Telescope. It is measured in billions of solar masses, not millions. Its shadow is so large that it became humanity's first direct visual sign of a black hole horizon. A dark center surrounded by light bent almost into a ring. TON 618 belongs above even that class. To move from Sagittarius A to TON 618 is not like comparing a house to a skyscraper. It is more like comparing a city to a continent. Sagittarius A is the dark heart of our galaxy, strong enough to control the motions of nearby stars. TON 618 is so massive that, if it were placed near the center of our solar system, the region around its event horizon would not be a local feature near the Sun. It would dominate scales normally reserved for the outer solar system. A black hole's event horizon grows in proportion to its mass. Double the mass, and the Schwarzschild radius doubles. For a black hole with tens of billions of solar masses, the radius can reach hundreds, or even over 1,000 astronomical units, depending on the exact mass estimate and spin assumptions. 1 astronomical unit is the average distance between Earth and the Sun. Neptune orbits around 30 astronomical units from the Sun. Pluto usually lies around 40 astronomical units away. The inner Oort cloud may begin far beyond that. TON 618 is the kind of black hole where the horizon scale itself can make planets feel like nearby dust, and the shadows seen around such a black hole can appear larger than the event horizon, because light does not simply travel in straight lines near extreme gravity. Photons curve. Some fall in, some loop around, some escape after being bent into a distorted image. NASA notes that TON 618's shadow is so wide that a beam of light would take weeks to cross it. That single fact is almost impossible to feel correctly. Light can cross the distance from Earth to the Moon in a little over a second. It reaches the Sun from Earth in about 8 minutes. But across the shadow of TON 618, light would need weeks. That is not a building-sized object. It is not a planet-sized object. It is not even star-sized in the familiar sense. It is a gravitational structure large enough to make the fastest thing in the universe feel slow. But size alone is not the whole reason TON 618 feels unreal. The deeper problem is growth. A black hole cannot simply decide to be huge. It has to become huge. It begins somewhere, maybe as the collapsed core of a very massive star, maybe as a direct collapsed black hole in the early universe, maybe as a heavy seed formed when gas collapsed under special conditions before fragmenting into ordinary stars, maybe through repeated mergers between smaller black holes inside growing galaxies. However the story begins, mass must be added. And adding mass takes time. A black hole feeding on gas faces a limit known as the Eddington limit. If matter falls in and releases radiation, that radiation pushes outward. Gravity pulls material inward, but light pressure can push material away. At a certain point, the outward pressure becomes strong enough to regulate the inflow. In simple terms, a black hole can become so bright while feeding that it begins to interfere with its own meal. This does not mean black holes never grow quickly. They can. Accretion can be messy. Gas can flow in through disks, streams, mergers, and unstable events. Some systems may exceed simple limits for periods of time. But the idea matters because TON 618 forces us to ask whether there has been enough time, enough fuel, and the right environment to build something so large. When we observe TON 618, we are not seeing it as it is today. We are seeing ancient light. The universe has expanded while that light traveled. Its wavelengths have stretched toward the red. The object's redshift tells us that the light comes from a much earlier cosmic age. The image we receive is not a live feed. It is a fossil signal from a younger universe, a message that has been traveling through space for billions of years. This is where the black hole becomes more than a record-breaking number. It becomes a clue about cosmic history. The early universe was not born with galaxies like the Milky Way already built. It began hot, dense, smooth in many ways, then expanded and cooled. Matter gathered into the first structures. Stars formed. Galaxies grew. Black holes appeared and began shaping their surroundings. For an ultramassive black hole to exist inside a bright quasar at high redshift, something in that history had to work efficiently. Gas had to reach the center. The host galaxy, or its ancestors, had to supply matter. Feedback had to avoid shutting the process down too soon. Mergers may have had to combine smaller black holes. The central engine had to keep feeding long enough to become monstrous. This is why the title says big enough to break reality. It does not mean TON 618 breaks the laws of physics. It means it breaks the easy version of reality that our imagination tries to use. We want black holes to be rare, compact monsters sitting at the centers of galaxies. We want the biggest ones to feel like exceptions we can place at the edge of a chart. But TON 618 refuses to stay neat. It pushes against the borders of what feels natural. If a black hole can become this massive, then galaxies are not just collections of stars. They are also growth machines for darkness. The host galaxy of TON 618 is difficult to see because the quasar is so bright. Imagine trying to study a candle next to a stadium floodlight, except the floodlight is the thing you are trying to understand, and the candle is the galaxy around it. The quasar's central glare can overwhelm the surrounding starlight. That means the black hole announces itself more clearly than the galaxy that feeds it. That reverses the usual intuition. Normally, we think of galaxies as the main objects, and black holes as hidden centers. With a quasar like TON 618, the center can overpower the city around it. The black hole becomes the visible face of the galaxy. The stars become the background. The engine becomes brighter than the machine it sits inside. To understand the physical scene, imagine approaching from impossible distance. At first, TON 618 is just a bluish point against blackness. As you move closer, the point becomes a nucleus, not because the black hole itself has appeared, but because the hot matter around it begins to resolve into structure. The accretion disk would be violent beyond any normal comparison. Material would orbit at a significant fraction of light speed. Heat would rise to levels that strip atoms apart. Radiation would flood nearby space. Magnetic fields could channel charged particles into enormous outflows. Nothing about this region would feel like an empty hole. A feeding, supermassive black hole is not quiet. It can shape its galaxy by injecting energy into surrounding gas. It can heat clouds, drive winds, and affect whether new stars form. The black hole is dark only at the boundary where escape ends. Outside that boundary, a quasar can be brighter than entire galaxies. That is one of the strangest contradictions in astronomy. The darkest possible object can power one of the brightest possible lights. The reason is efficiency. Matter falling toward a black hole can convert a large fraction of its rest mass energy into radiation before crossing the horizon. Depending on the black hole's spin and disk structure, ordinary nuclear fusion in stars is powerful, but accretion onto a black hole can be even more efficient at turning mass into light. That is why a relatively compact region near a black hole can outshine a galaxy filled with hundreds of billions of stars. TON 618 is not terrifying because it is a big empty sphere. It is terrifying because the region around it would be a place where gravity turns motion into radiation on a scale that seems excessive even for the universe. But there is another piece of the story, and it is easy to misunderstand. A huge black hole does not automatically mean the tidal forces at the event horizon are stronger than those of a small black hole. In fact, for very massive black holes, the tidal gradient at the horizon can be weaker. Tidal force depends on how quickly gravity changes across your body. A small stellar mass black hole has a tiny horizon, so gravity changes sharply over short distances. Falling feet first toward one could stretch you violently before or near the horizon. For an ultramassive black hole, the horizon is so large that the change in gravity over human scale at the boundary could be relatively gentle. This creates an eerie possibility. If you somehow fell toward a black hole like TON 618, ignoring the fatal radiation and environment around an active quasar, the event horizon itself might not be marked by instant spaghettification. You could cross a mathematical boundary where escape becomes impossible without feeling a sudden wall. Outside observers would never see you cross in the ordinary way. Your light would fade and redden. But from your own perspective, the local crossing could be quiet. That quietness makes it worse. The event horizon is not a surface that burns you. It is not a glowing shell. It is a causal boundary. After crossing it, all future paths lead inward. The terrifying part is not impact. It is direction. Space and time are arranged so that moving forward inevitably means moving deeper. TON 618 enlarges that idea until it becomes architectural. Its horizon is not a small trapdoor. It is a vast region of no return. Once inside, the central singularity, or whatever quantum gravity replaces it with, is not just somewhere in space, it lies in your future. That is why black holes are not simply objects. They are changes in the structure of possible motion. And with TON 618, the structure is on a scale so large that ordinary astronomical distances become interior concepts. Still, we must be careful with the word singularity. General relativity predicts that matter inside a classical black hole collapses toward a region of extreme curvature. But physicists do not believe our current theories are complete there. At the smallest scales and strongest gravities, quantum effects should matter. We do not yet have a finished theory of quantum gravity. So when a documentary says that TON 618 contains a singularity, it is really saying that our best classical theory points toward a place where the theory itself stops being enough. That is another way TON 618 breaks reality. Not because it violates physics, but because it leads us to the edges of physics. The event horizon can be described, The mass can be estimated. The radiation from nearby matter can be measured. The redshift can be recorded. But the deepest interior remains beyond direct observation. Nature has placed a curtain around the most extreme part of the object. And the curtain is not made of dust or distance. It is made of causality. No telescope can look through an event horizon. No message can come back from inside. No probe, no matter how advanced, could return data after crossing. This means the largest black holes in the universe are also some of the most private places in reality. They affect everything around them, but their interiors are locked away. TON 618 can shout across billions of years as a quasar, yet the part that defines it most completely is silent forever. That silence matters because it separates what we can imagine from what we can test. We can calculate the horizon scale. We can model the disk. We can compare luminosity. We can measure spectral lines. But beyond a certain boundary, information stops participating in the outside universe. Black holes do not merely hide objects. They remove events from future communication with us. Now place that idea next to the mass again. More than 60 billion suns. A shadow light takes weeks to cross. A quasar bright enough to overwhelm its galaxy. A signal arriving from billions of years in the past. A gravitational boundary that no future observation can penetrate. This is why TON 618 is not just another big thing. It is a combination of scale, distance, brightness, age, and hiddenness. Any one of those would make it interesting. Together, they make it feel almost unreasonable. But the universe is not required to fit human reason. It only has to fit its own laws. And the laws, in this case, allow a black hole to become so massive that it turns comparison into a problem. If you try to compare TON 618 to the Earth, the scale disappears. Earth becomes too small to matter. If you compare it to the Sun, even the Sun becomes a unit, repeated tens of billions of times. If you compare it to Sagittarius A, you discover that the black hole at the heart of our entire galaxy becomes only a smaller example. If you compare it to the solar system, the horizon scale begins to swallow the map. If you compare it to human time, the crossing time for light alone becomes longer than many things we consider normal journeys. So we need a different way to picture it. Start with the Sun. The Sun is about 1.4 million kilometers across. It can hold more than 1 million Earths by volume. Its gravity binds planets, asteroids, comets, and dust into a system that extends far beyond Neptune. The Sun is so dominant that nearly everything in our neighborhood orbits it. Now imagine replacing the Sun, not with a black sphere the same size, but with a gravitational object whose event horizon radius stretches across hundreds or more astronomical units. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, the Kuiper Belt, and many known distant objects would lie on scales that no longer feel safe or separate. The familiar solar system would become a small diagram beside a much larger darkness. This is not a realistic scenario for TON 618 appearing here. It is a scale exercise. But it helps because numbers alone fail. Humans are good at imagining landscapes, rooms, roads, oceans, and mountains. We can stretch that imagination to planets. We can learn to accept stars. But a black hole like TON 618 belongs to a category where the object is not merely large. It forces familiar systems to become measuring marks. The solar system becomes a ruler. The Sun becomes a grain of mass. The speed of light becomes a slow crawl across the shadow. That is why black hole-size animations often end with TON 618. It sits at the end not because nothing larger can ever exist, but because known candidates like it occupy a scale where the viewer's sense of comparison has been exhausted. By the time you reach it, You have already passed stellar black holes, intermediate black holes, the Milky Way's central black hole, and giant elliptical galaxy black holes. TON 618 appears as the final escalation. But a useful documentary cannot stop at escalation. It has to ask what this thing is doing to its surroundings. A black hole does not grow alone. The mass has to come from somewhere. In the case of a quasar, that somewhere is a galactic environment rich enough to funnel matter inward. Gas loses angular momentum. It falls toward the central region. Collisions, turbulence, bars, mergers, and gravitational interactions can disturb material and send it toward the nucleus. The accretion disk forms because matter cannot simply drop straight in. It has sideways motion. It orbits, heats, radiates, and slowly moves inward through friction and magnetic processes. Near TON 618, that disk would not be a gentle ring. It would be an ecosystem of plasma under extreme gravity. Different parts of the disk orbit at different speeds. Inner regions race faster than outer regions. Energy is released unevenly. Radiation pressure pushes outward. Magnetic fields may lift material away. Winds can carry gas back into the host galaxy. Some matter reaches the horizon. Some is expelled. Some glows from far enough away to produce broad emission lines that astronomers can use to infer mass. This is the feeding process made visible. And feeding can fight itself. A growing quasar does not simply consume everything around it like a drain in water. The energy released by accretion can heat the surrounding gas and make it harder for more gas to fall in. This feedback can regulate black hole growth and galaxy evolution. In some galaxies, active galactic nuclei may help shut down star formation by heating or ejecting gas. In others, shocks and compression may trigger local changes. The details are complex, but the main idea is that a feeding black hole is not only a passenger inside its galaxy. It can become an actor. TON 618, as a hyperluminous quasar, represents that actor in an extreme form. It is not just eating, it is changing the stage around it. If the central black hole is over 60 billion solar masses, its host galaxy and surrounding environment must have a history capable of delivering extraordinary fuel. That history is partly hidden by distance and glare. We do not have a nearby, clean, beautifully resolved view of the system. We have light filtered by cosmic expansion and interpreted through instruments. The quasar is both a beacon and a barrier. It tells us something enormous is there. It also makes the details harder to see. That is another reason it feels like a broken piece of reality. The object is too bright for its own surroundings. It reveals itself by hiding the galaxy that produced it. Now consider what it would mean to exist near such an object. A planet in the quasar's inner environment would not be a gentle world under a normal night sky. Radiation would dominate. The accretion disk could flood nearby space with high-energy light. Jets, if present and pointed in certain directions, could be catastrophic along their path. Gas clouds would be ionized. Stars near the central region would move through a gravitational landscape shaped by an immense mass. Even at great distances, the quasar could be the brightest thing in the sky. But close to the black hole, ordinary planetary stability becomes a fragile idea. The problem is not only falling in, it is surviving the environment outside. This matters because black holes are often imagined as vacuum cleaners. That is misleading. A black hole does not reach out and suck in everything across the universe. If the Sun could be replaced by a black hole of the same mass, Earth would continue orbiting at roughly the same distance, though it would lose sunlight and die for other reasons. Gravity at a distance depends mainly on mass, not on whether the mass is a star or a black hole. But TON 618 is not frightening because it magically sucks harder than gravity allows. It is frightening because its mass is so enormous and because an active quasar environment adds radiation, heat, winds, and violent matter flows to the gravitational picture. That distinction makes the fear more realistic. A black hole is not a fantasy monster. It is a region of space-time. A quasar is not magic fire. It is matter losing energy as it falls inward. The horror comes from the laws working correctly at a scale that does not care whether we can comfortably imagine it. The question then becomes, how did we even find it? TON 618 entered astronomy not as a dramatic photograph of a black hole, but through surveys of blue and radio-bright objects. Early quasars were confusing because they looked star-like, but had unusual spectra and strong redshifts. Once astronomers realized quasars were distant active galactic nuclei, the faint blue points on photographic plates became something much stranger: luminous engines at cosmological distances. The name TON comes from the Tonant-Sintler catalogue, connected to observations of blue objects. The number 618 is simply an entry. That ordinary catalogue label now points toward an object so extreme that it shows up in black hole-size comparisons around the world. There is something almost unsettling about that. One of the largest known black holes has a name that sounds like a file number, not a mythological beast, not a warning. Just TON 618. Astronomy is full of this contrast. The universe gives us objects that feel beyond imagination, and we give them catalogue names, coordinates, redshifts, magnitudes, and spectral lines. We turn terror into tables. That is how science survives contact with scale. It does not need the universe to become smaller. It builds ways to measure what cannot be held in the mind all at once. But even the measurements raise problems. When astronomers estimate black hole masses in quasars, they often rely on relationships involving the broad-line region. The broad-line region is gas moving rapidly under the black hole's gravity, producing emission lines that are widened by motion. If you know the velocity of the gas and the size of the region, you can estimate the central mass. For many active galactic nuclei, reverberation mapping can connect changes in the central light to delayed responses in the gas, giving a size estimate. For more distant quasars, single-epoch methods use luminosity and line widths calibrated by those relationships. This is powerful, but not perfect. Geometry matters, orientation matters, the structure of the gas matters, the quasar's brightness and variability matter. That is why a mature script about TON 618 should not pretend the number is as direct as weighing a rock on a scale. The mass is extraordinary, but the path to that mass involves interpretation. Scientists accept uncertainty not because they are weak, but because the universe is complex and honesty is part of precision. For TON 618, the key point remains. Even if the exact mass estimate changes with future observations, the object is still in the ultramassive class. It is still among the largest known black hole candidates with direct measurement methods. It still represents a scale far beyond ordinary supermassive black holes. In other words, uncertainty does not rescue our intuition. It only makes the monster slightly blurry around the edges. The next problem is the age of the light. When light from TON 618 left its source, the universe was younger. The galaxy hosting it, the gas around it, and the black hole itself belonged to an earlier chapter of cosmic history. Since then, the universe has expanded. Other galaxies have evolved. Stars have lived and died. The quasar we see may not be active in the same way now, because now is not what we are seeing. This is a deeply strange part of cosmology. Looking far away means looking back in time. TON 618 is not merely distant in space, it is distant in history. We do not observe it across a normal gap like watching a mountain across a valley. We observe it across cosmic time, with expansion stretching the path between emission and reception. The light carries an ancient record of an object that may have changed completely by the present era. The black hole might have grown larger. It might have slowed its feeding. The quasar might have faded. The host galaxy might have merged. The central engine might have entered a quieter state. We cannot simply check. The present condition of TON 618 is hidden by time. Any new information from its present state would need billions of years to reach us. In that sense, TON 6018 is not only sealed by an event horizon, it is also separated by the age of its own light. That double separation gives it an almost ghost-like quality. We see the bright past of an object whose deepest center cannot send information outward, and whose current state is not yet visible to us. A black hole already hides its inside. Cosmic distance hides its present. Together, they make TON 618 feel less like a place and more like a message from a part of reality we can never fully enter. Still, the message is rich. Its existence tells us that the universe can create black holes far more massive than the one at the center of our galaxy. It tells us that some galaxies or proto-galaxies can funnel gas into their centers on enormous scales. It tells us that quasars are not just lights in the sky. They are episodes in the coevolution of galaxies and black holes. It tells us that the early and middle universe contained engines so bright that they can still be detected across billions of light years. And it tells us that the quiet sky is deceptive. If you stand under a clear night and look up, you do not see TON 618 with your eyes. You see nearby stars, the moon, perhaps a planet, maybe the Milky Band of our own galaxy if the sky is dark enough. The most extreme objects are often invisible to ordinary sight. The universe does not announce its largest structures in a way scaled for humans. It takes instruments, spectra, redshift measurements, radio surveys, X-ray observations, infrared data, mathematical models. Only then does the faint point become a quasar, and the quasar become a black hole, and the black hole become one of the most massive gravitational objects known. That transformation from dot to monster is one of the great powers of astronomy. It teaches us that the sky is not what it appears to be. But it also raises a more uncomfortable question. If TON 618 exists, what else exists beyond our present ability to measure? The largest known object in a category is rarely guaranteed to be the largest that nature can make. It is usually the largest we have found, under the selection effects of our instruments and surveys. The universe is vast, ancient and unevenly observed. Some black holes may be hidden behind dust. Some may be inactive, and therefore much harder to detect. Some may sit in galaxies where direct measurement is not possible from Earth. Some may be beyond the horizon of what current instruments can resolve. TON 618 may not be the final answer. It may be a warning that the answer is larger. That is a different kind of terror from direct danger. TON 618 will not chase Earth. It is not a threat to the solar system. Its gravity does not reach across billions of light years to pull us in. The fear is intellectual. It is the realization that human categories are provisional. We build charts, and then the universe places something at the edge of them. We extend the chart, and the edge moves again. Black holes began as mathematical consequences. Then they became astrophysical objects. Then we found stellar black holes. Then supermassive black holes. Then quasars at huge distances. Then ultramassive black hole candidates that make even galactic centers feel modest. TON 618 sits in that escalation. But to understand why it may be difficult for nature to build many more objects like it, we have to talk about the upper limits of growth. A black hole can grow by accreting matter or by merging with other black holes. Both processes face obstacles. Gas has angular momentum. It does not fall inward easily. Radiation from the accretion process can push gas away. Feedback can heat the environment. Mergers take time and depend on galaxy interactions. Extremely large black holes may struggle to keep forming stable accretion disks because the relevant disk scales become enormous, and self-gravity can cause the disk to fragment into stars before matter reaches the center efficiently. This is one reason ultramassive black holes are rare. The universe may allow them, but it does not create them casually. To build TON 618, a galaxy needed a special history. It likely needed repeated access to fuel, deep gravitational wells, and conditions that kept feeding the central black hole over long periods. It may have involved mergers, gas-rich phases, and a host environment we cannot fully reconstruct from here. The object is therefore not only large, it is the outcome of a long chain of successful growth events. Miss one link, and the monster may never form. That gives TON 618 a historical weight. It is not just a black hole in space, it is a record of everything that happened around it before the light we see was emitted. Every gas flow, every galaxy interaction, every burst of accretion, every feedback episode contributed to the final mass we infer. The black hole is like a cosmic bank account containing the deposits of a violent galaxy history. And unlike a star, it does not shine by burning itself away in the same way. A star balances gravity with fusion. It has a life cycle tied to fuel in its core. A black hole's mass is not spent to shine. The quasar shines because outside matter falls in. The black hole can grow while the surroundings blaze. The engine becomes heavier as the visible event becomes brighter. This is one reason quasars mark powerful growth eras. They are not just lamps. They are feeding records. When a quasar is bright, it means matter is moving violently toward a central black hole. The luminosity tells us about accretion. The line widths tell us about motion. The redshift tells us when in cosmic history the light began. The whole object becomes a puzzle where brightness, distance, velocity, and mass are connected. TON 618 is one of the extreme puzzles. Now imagine the sky from a safe fictional world, far from the direct danger, but close enough that the quasar dominates the heavens. There would be no ordinary night. The central quasar could appear as a fierce point or blazing core, depending on distance and dust. Surrounding gas might glow in enormous structures. The black hole itself would remain invisible, but its environment would announce its presence everywhere. Space would not feel empty. It would feel energized, ionized, and unstable. If the planet were inside a galaxy hosting such an active nucleus, life would depend heavily on distance, shielding, atmosphere, magnetic fields, and the direction of jets or radiation. Too close, and high-energy radiation could strip atmospheres, damage chemistry, or sterilize surfaces. Farther out, the quasar might become a bright, but survivable feature, perhaps shaping climate or sky brightness in ways no Earth-like world has experienced. This is speculative, but it gives the scale a living context. TON 618 is not just a number in a table. If worlds existed in its wider host galaxy, their skies and histories could be shaped by the central engine. A galaxy with an active quasar is a galaxy where the core is not asleep. Our own Milky Way's central black hole is quiet today by comparison. Sagittarius A occasionally flares, but it is not a quasar. It is underfed. The Milky Way is not currently blazing from its center. If it were, the night sky and radiation environment of parts of the galaxy could be very different. That comparison helps show how extraordinary quasars are. They are not normal galactic centers with a little extra light. They are extreme feeding states. TON 618 is an extreme feeding state around an extreme black hole. That double extremity is why the object has become famous. But fame can also flatten it into a meme. Online, TON 6018 often appears as simply the biggest black hole, the black hole that could swallow the solar system, the object that makes all other black holes look small. Those comparisons are useful for shock. They are not enough for understanding. The real story is better. An ancient, hyperluminous quasar, an ultramassive black hole measured through the motion of gas. A shadow light would take weeks to cross. A central engine so bright it hides its host. A growth history that challenges easy models. An event horizon that turns enormous regions of space into one-way future. That is much stronger than a simple size contest, because a size contest ends when something bigger is found. A physical story lasts longer. Even if future measurements revise TON 618 downward or upward, the reason it matters remains. It shows what happens when gravity, gas, time, and galaxy evolution work together at the highest levels. It is a case study in how the universe builds extremes. There is also a quieter fact about TON 618 that often gets buried under the mass comparison. The black hole is not the largest structure connected to the system. Around quasars, gas can extend far beyond the central engine. Some quasars are surrounded by huge reservoirs of hydrogen that glow through Lyman alpha emission, a form of ultraviolet light produced when electrons in hydrogen atoms change energy levels. Because TON 618 is so distant and redshifted, features like this become part of the evidence astronomers use to understand the environment around it. The black hole is the central monster, but it lives inside a much larger cosmic neighborhood of gas, radiation, and galactic structure. This matters because it changes the picture from a single dark ball to a whole system. At the center is the event horizon. Around that is the region where light paths are severely bent. Beyond that is the accretion disk and the broadline region. Farther out are gas clouds, winds, and the hidden host galaxy. Farther still is the cosmic web that delivered matter into the galaxy across time. So TON 618 is not only a black hole with a frightening mass, it is the center of a hierarchy. Every layer tells a different part of the story. The event horizon tells us about no return. The shadow tells us about curved light. The disk tells us about energy. The broad emission lines tell us about speed and mass. The surrounding gas tells us about the galaxy's supply of matter. The redshift tells us about the age of the light. A weak script would only repeat that TON 618 is big. A stronger one asks what each layer is doing. Start with the shadow. The shadow of a black hole is not the physical surface of the event horizon. It is the dark region created because light from behind and around the black hole is captured or bent away from the observer. The actual image depends on the black hole's spin, the viewing angle, the material around it, and how light travels through curved space-time. For a black hole like TON 618, the shadow becomes a cosmic scale effect. It is not a small circular stain. It is a region so wide that light itself takes weeks to cross it. Now move outward to the photon region. Near a black hole, there can be paths where photons orbit temporarily before escaping or falling in. These paths are unstable. A slight disturbance sends the light away or inward. In images like that of M87, the ring-like glow is connected to light from hot material bent around the black hole by gravity. TON 618 is too distant for us to image in that way with current tools. But the physics matters. Around an ultramassive black hole, the stage on which this light bending happens is stretched to outrageous scale. Then comes the disk. An accretion disk is often drawn as a smooth, glowing ring, but that picture is too clean. Real disks can be turbulent. They can have clumps, magnetic structures, hot inner regions, cooler outer regions, and winds leaving the surface. The inner disk can convert gravitational energy into radiation with incredible efficiency. In a quasar, The disk is not just a decorative feature, it is the power plant. Without infalling matter, the black hole would be dark. With enough matter, it becomes the engine behind a beacon visible across the universe. TON 618, therefore, has two identities at once. As a black hole, it is a place where light cannot escape. As a quasar, it is a source of light powerful enough to cross billions of years and still reach our telescopes. That contradiction is not poetry. It is a physical process. Matter loses energy as it spirals inward. That energy leaves as radiation before the matter crosses the horizon. The black hole does not shine from inside. The falling universe shines on the way down. This helps explain why the object can be famous even though nobody has photographed its event horizon directly. We know it through its effects. Most of astronomy works this way. Neptune was understood through gravity before it became a visible disk in telescopes. Exoplanets are often found by the dimming or wobbling of their stars, not by direct pictures. Dark matter is inferred from gravitational behavior, not from light. Black holes, especially distant active ones, are measured through the violence of their neighborhoods. The universe often reveals the invisible by disturbing the visible. TON 618 is one of the most extreme examples. Its gravity organizes gas at speeds that broaden spectral lines. Its feeding produces brightness that outshines the host. Its distance stretches its light. Its mass enlarges its horizon. None of these clues alone would be enough to make the full image feel real. Together, they point toward a central engine that belongs near the top of the known black hole scale. The next useful comparison is not another black hole, but time. A human lifetime is usually measured in decades. A civilization can change dramatically in centuries. Written history covers only a few thousand years. The light from TON 618 has been traveling for billions of years. During that journey, Earth changed again and again. Continents moved. Life evolved. Species appeared and vanished. Long before humans built telescopes, long before mammals dominated the planet, long before almost everything familiar existed, the light now entering our instruments had already begun crossing space. This means TON 618 is not only a distant object, it is older than our questions about it. The signal did not know it would become a data point in a human observatory. It did not know a species would evolve on a small rocky planet, build glass lenses, launch space telescopes, and argue about how large a black hole can become. It simply traveled. It crossed expanding space until a few photons landed in detectors and became evidence. There is something humbling about that. But the important part is not emotion. The important part is method. Because the light is old, the object is a probe of an earlier cosmic era. Because it is bright, we can study it despite the distance. Because its central black hole is huge, it tests ideas about growth. TON 618 is useful not because it is famous online, but because it sits at the intersection of extreme mass and cosmic time. A small black hole nearby would teach one set of lessons. A giant black hole in the modern universe would teach another. An ultramassive quasar seen billions of years in the past teaches something stranger. The universe had already built monsters while it was still writing earlier chapters of galaxy evolution. This is where the growth problem becomes sharper. Suppose a black hole begins as a stellar remnant, maybe 10 or 100 solar masses. To reach tens of billions of solar masses, it must grow by an absurd factor. If it grows steadily at the Eddington rate, the mass can increase exponentially over time. But each E-folding takes a certain amount of time depending on efficiency. Start with a small seed, and you need many doublings. Start with a heavier seed, and the path becomes easier. Allow super Eddington phases, and the path changes. Add mergers, and the story becomes more complex. No single simple path is guaranteed for every monster black hole. That is why early and ultramassive black holes, remain an active research problem. Scientists are not asking whether black holes can grow. They clearly can. They are asking which combination of seed mass, accretion physics, galaxy mergers, and feedback can build the largest observed systems by the times at which we see them. TON 618 is part of that pressure. It is one thing to say black holes grow over cosmic time. It is another to find one so massive that the ordinary growth story feels strained. The solution may not require new laws. It may require better details. Perhaps the seeds were larger than simple stellar remnants. Perhaps early gas flows were more efficient in some environments. Perhaps mergers occurred in dense regions. Perhaps accretion episodes were more intense or more sustained than simple models assumed. Perhaps our measurements will be refined. Each possibility changes the path, but none makes the object boring. This is why the phrase "break reality" should be understood carefully. In science, an object does not become exciting by breaking the universe. It becomes exciting by breaking the simplified picture in our heads. The universe itself remains consistent. Our models adapt. The frightening part is discovering that the simplified picture was too small. TON 618 is not a glitch. It is a demand for a more complete explanation. And complete explanations are often less comforting than simple ones. A simple explanation says black holes grow slowly, and the largest ones sit quietly in old galaxies. The more complete explanation says black holes can feed violently, shine across the observable universe, regulate their galaxies, hide their hosts, distort light, challenge growth models, and seal their interiors forever behind horizons. That is not waffle. That is a chain of physical consequences. There is also a common question people ask when they hear about TON 618. Could it destroy us if it were closer? The answer depends entirely on what closer means. If TON 618 were somehow placed near the solar system would not remain recognizable. Its gravity would dominate the region. Planetary orbits would be wrecked. The sun would no longer be the central anchor. But this is not a realistic threat, because TON 618 is cosmologically distant. It is not wandering toward Earth as a danger. Its relevance is not survival in the direct sense. The realistic danger of TON 618 is not physical proximity. It is perspective. It reveals that objects exist which make our local cosmic environment seem gentle and small. The sun feels powerful because it defines every day on Earth. Sagittarius A feels enormous because it anchors the center of our galaxy. But TON 618 belongs to a universe where even those reference points become steps on a ladder. That is why a good visual for this episode would not show a black hole chasing Earth. It would show the Earth, then the Sun, then the Solar System, then Sagittarius A, then M87, then the shadow scale of TON 618, each layer shrinking the previous one until the viewer no longer feels that the first comparison was useful. The horror comes from scale correction. The viewer realizes the mental map was too small from the beginning. But even that visual has a problem. Black holes are not solid balls. Showing them as spheres is a teaching tool, not a literal photograph. The event horizon is a boundary in space-time. The shadow is an optical effect. The accretion disk can be tilted and warped. The actual appearance depends on light, plasma, relativity, and viewing angle. So the more accurately we describe TON 618, the less it behaves like an ordinary object. It is not simply a thing in space. It is a region where space, time, light, and matter all stop behaving in familiar ways. That is the real reason it fits the channel. TON 618 is not just big, it is an entry point into gravity itself. Through it, we can talk about how black holes are measured, how quasars shine, how galaxies feed their centers, how the early universe built extreme structures, how light carries ancient information, why horizons hide interiors, and why size becomes strange when the object is made from curved space-time rather than ordinary material. A rock can be large, a star can be large, a nebula can be large. A black hole like TON 618 is large in a more disturbing way, because its size is partly a statement about what can no longer communicate with the outside universe. Its horizon is not just a surface, it is an ending for every path that crosses it. And outside that ending, the quasar keeps shining. That combination is what makes the object unforgettable. A silent center surrounded by a scream of radiation, an invisible boundary wrapped in one of the brightest lights in the cosmos. And the next part of that story leads toward a question even more unsettling than size. What would it actually be like to move near an object like this? Not as a number, but as a journey. Not to cross the event horizon immediately, not to fall into the singularity in one dramatic scene, but to approach from far outside the quasar, passing through the galaxy, the glowing gas, the radiation fields, the disk environment, and the gravitational zones where normal intuition begins to fail. Because TON 618 is not terrifying only from a chart. It is terrifying when we treat it as a place where the black hole is not a point, but a region, a place where light bends before it vanishes, a place where time changes its behavior near the horizon, a place where the brightest object in the surrounding universe is powered by the darkest boundary inside it. And that is where the first half of this journey has to end. Outside the monster, still far enough away to see its light, but close enough to understand that the dot in the telescope was never small. It was only waiting for us to learn how to read it. To read it properly, we have to move inward, not straight into the black hole. That would be too simple, and in a place like TON 618, even the word simple begins to break down. We have to begin outside the quasar, far from the central engine, where the light has already spread into the surrounding universe, and the object still looks almost peaceful. From that distance, TON 618 would not announce itself as a monster. It would not look like a hole carved into space. It would look like a violent star that refuses to behave like any normal star. A single point of light, burning too brightly, shining from a galaxy so far away that its photons left when the universe was much younger than it is now. That is the first trap. The object looks small because distance has crushed it into a dot. But the dot is not the thing. The dot is only the signal. Behind that signal is a region of space where gas, dust, gravity, radiation, and time are being forced into one of the most extreme arrangements nature allows. A normal star glows because nuclear fusion is happening in its core. A quasar glows because matter is being destroyed by motion before it falls into darkness. The black hole itself gives off no light. The event horizon is not a surface you can see. The brightness comes from the material still outside it, material moving so violently that gravity turns falling matter into one of the most powerful engines in the universe. So as we imagine moving closer, the first thing that changes is not the size of the black hole. It is the environment. The background does not remain quiet. The ordinary darkness around deep space becomes filled with heat, charged particles, magnetic fields, and radiation. The galaxy hosting TON 618 may be hidden by the quasar's brightness from our distant point of view, but near the object itself, that galaxy would not be empty. Somewhere there would be stars. Somewhere there would be gas clouds. Somewhere there would be dust being stripped, heated, compressed, and pulled toward the center. And near the core, the quasar would dominate everything. A galaxy can contain hundreds of billions of stars, but a feeding black hole can outshine the galaxy around it. That does not mean the black hole is giving off light like a lamp. It means the black hole has created a place where matter cannot fall gently. Imagine gas drifting toward the center of a galaxy. At first, it may move slowly, part of a vast cloud shaped by gravity and collisions over millions of years. But as it loses energy, it spirals inward. It cannot simply drop straight into the black hole because it has angular momentum. It circles, it squeezes, it rubs against other gas. Friction and turbulence turn orbital motion into heat. The gas becomes a disk, and the closer it moves to the center, the faster it must travel. In the outer regions, the disk may already be hotter than most places in the universe. Closer in, it becomes a furnace. Closer still, it becomes something no ordinary furnace on Earth can explain. The accretion disk around a quasar is not a solid ring. It is not a smooth plate. It is a storm of plasma, a flat but chaotic river of charged particles sliding around the black hole at enormous speed. Magnetic fields thread through it. Radiation pushes back against it. Gravity pulls down on it. The disk feeds the black hole, but not cleanly. Some matter falls inward. Some matter is blown away. Some becomes part of winds that can rush out from the center and affect gas far beyond the galaxy's core. That is one of the reasons TON 618 is not just a large black hole. It is an active system. A dead, supermassive black hole can sit quietly in the center of a galaxy, enormous but dim, revealing itself only through the orbits of nearby stars. A quasar is different. It is a black hole during a feeding phase. It is not asleep. It is turning falling matter into a beacon. The terrifying part is that the beacon can make the black hole harder to understand. The brighter the quasar becomes, the harder it is to see the galaxy underneath it. The light that helps us find TON 618 also hides the full environment around it. It is like trying to understand a city at night by staring directly into a searchlight. You know something powerful is there, but the brightness destroys the details. So scientists have to read the spectrum. They look at the light split into its colors. They study emission lines from gas surrounding the black hole. They measure how broad those lines are, because broader lines often mean faster-moving gas. And faster-moving gas near a quasar usually means stronger gravity. This is where the mass estimate comes from, and it is also where the uncertainty begins. TON 618 has often been described with a mass around tens of billions of suns. Older estimates placed it near 66 billion solar masses. Other analyses have suggested a lower, but still extraordinary value, around 40 billion solar masses. Either number is far beyond the black holes we usually imagine. Either number makes it ultramassive. Either number makes the event horizon so large that comparing it to planets stops being useful. But that uncertainty matters. It reminds us that TON 618 is not an object we can fly around and measure with a spacecraft. It is an object measured through ancient light, line widths, models, assumptions, and distant radiation. Its size is not something we have touched. It is something inferred from the behavior of gas in a system more than 10 billion light-years of look-back time away. And yet, the conclusion remains. Whatever the exact number is, TON 618 is enormous enough that the event horizon would be wider than the inner solar system by a staggering margin. If you tried to draw it at the center of our solar system, the dark boundary would not fit neatly between the Sun and Mercury. It would not stop near Earth. It would not even feel limited by the worlds we usually use for scale. Depending on the mass estimate, the radius of the event horizon would reach hundreds to over 1,000 astronomical units. That means the boundary around the black hole could extend far beyond the orbit of Pluto. The darkness would not be a point at the center. It would be a region large enough to replace the solar system's architecture with a single gravitational ending. And still, this is only the event horizon. The influence reaches farther. The accretion disk, the broadline region, the glowing gas, the winds, and the surrounding halo do not stop at the edge of the black hole. They form a larger environment, and that environment is what a traveler would face long before reaching the horizon itself. So the next stage of the journey is not falling, it is surviving the approach. A spacecraft approaching a quasar like TON 618 would not be destroyed first by the black hole's surface, because there is no surface. It would face radiation. It would face particle storms. It would face hard light from gas heated to extreme temperatures. It would pass through regions where the sky ahead is not dark, but blinding, where invisible radiation carries more danger than visible glow, where shielding becomes the difference between a mission and immediate failure. In ordinary space travel, distance is the enemy. Near a quasar, brightness can become the enemy. That sounds backwards because black holes are supposed to be dark, but the surrounding matter can be so luminous that the black hole becomes the engine behind one of the brightest objects known. TON 618 is not terrifying because it is invisible. It is terrifying because the invisible center is surrounded by so much visible violence that the light itself becomes a warning. If Earth were placed at a safe-looking distance, the quasar might still flood space with radiation. If a planet existed too close, its atmosphere could be stripped, heated, and chemically altered. If gas clouds orbited nearby, they could be blown outward by quasar winds. If stars moved through the central region, their outer layers might be disturbed by tides, radiation, or collisions with dense gas. The quasar is not just sitting in its galaxy, it is affecting the conditions around it. This is one of the biggest differences between black holes in fiction and black holes in real astrophysics. Fiction often treats them as mouths that only matter if you get close enough to be swallowed. Real, supermassive black holes can influence galaxies without eating everything. They heat gas, they launch jets, they drive winds, they regulate star formation. They can prevent gas from cooling into new stars or blast material out of a galaxy's core. A black hole can shape a galaxy without consuming the galaxy. TON 618 shows that idea at an extreme scale. The object is so luminous that it tells us matter is being processed around the black hole at an incredible rate. The quasar's energy output implies a central engine that is not merely large but active, efficient, and surrounded by enough fuel to keep the system blazing. That raises a question that becomes more disturbing the longer we stay with it. How did something like this grow? A black hole does not become tens of billions of solar masses by accident. It has to gain mass. It can grow by swallowing gas. It can grow by merging with other black holes. It can sit at the center of massive galaxies, where material is funneled toward the core. But there are limits. If gas falls in too quickly, radiation from the hot accretion disk pushes outward. This outward pressure can resist further inflow. In simple terms, a feeding black hole can become so bright that its own light pushes away some of its food. That balance is connected to the Eddington limit. The Eddington limit is not a magical wall, but it is a crucial idea. It describes a balance between gravity pulling material inward and radiation pressure pushing material outward. A black hole can grow rapidly, but if it shines too intensely, the light from the accreting gas can drive material away. That makes extremely massive black holes a cosmic puzzle, especially when they are observed in the early universe. TON 618 is seen as it was billions of years ago. Its light has traveled for an enormous fraction of cosmic history. That means the black hole was already ultramassive when the universe was younger. So the question becomes, did it begin from a smaller seed and feed with extraordinary efficiency, or did it start from a much larger seed than ordinary stellar collapse would produce? Did dense, early gas clouds collapse directly into massive black hole seeds? Did repeated mergers build it quickly? Did its host galaxy provide a rare environment where growth could continue for a long time? Or are our estimates missing something about the geometry of the gas? The terrifying part is not that we have no ideas. It is that every idea forces the early universe to be more extreme than it first appears. A normal stellar black hole, formed from the death of a massive star, might begin with a few solar masses, or perhaps dozens. Even if it feeds, it must grow through time. To reach billions of solar masses by early cosmic epochs, some black holes must have lived in environments that gave them extraordinary advantages. They may have been born massive. They may have fed almost continuously. They may have merged inside crowded proto-galaxies. They may have grown through processes we are still trying to model. TON 618 is not only big, it is evidence that the universe can build enormous darkness while everything else is still young. That is one reason the title says it is big enough to break reality. Not because the black hole literally breaks physics, but because it breaks ordinary expectation. We expect size to come slowly. We expect the early universe to be unfinished. We expect monsters to need time. But quasars show us that in some places, the young universe was already capable of building engines bright enough to be seen across billions of light years. And TON 618 pushes that feeling to the edge. To understand the scale, we can imagine crossing the event horizon from far outside. Not because anyone could survive the full environment around an active quasar, but because the geometry itself reveals something strange. Around a small black hole, tidal forces near the event horizon can be catastrophic. The pull on your feet and your head can differ so strongly that you are stretched apart before crossing. This is often called spaghettification. But around an extremely massive black hole, the event horizon can be so large that the tidal gradient at the boundary is much weaker. You might cross the horizon without feeling a sharp tearing force at that exact line. That sounds almost gentle. It is not. It only means the danger has changed shape. The event horizon is not a wall. It is a boundary in space-time. Outside it, paths can still lead away. Inside it, every possible future path leads deeper inward. If TON 618 has an event horizon hundreds or more than 1,000 astronomical units in radius, crossing it would not feel like entering a small tunnel. It would be like passing a boundary larger than the planetary region of a star system. There would be no bright surface to warn you. There would be no sudden impact. If you crossed in darkness, you might not know from local sensations that you had passed the point of no return. The outside universe could still appear around you for a while. Light from behind could still fall inward. Signals you sent outward would fail to escape. But locally, nothing may flash red and declare that reality has changed. That is one of the most disturbing things about event horizons. They are not frightening because they are dramatic. They are frightening because they are final. From far away, an object falling toward the event horizon appears to slow and fade because of gravitational time dilation and redshift. Its light stretches, weakens, and takes longer to reach observers outside. But from the falling object's own point of view, it crosses the horizon in finite time. These two descriptions are not simple contradictions. They are different perspectives in curved space-time. Near TON 618, the scale makes those ideas almost impossible to visualize. Time does not break, but our intuition does. We live in a world where gravity is weak, where clocks mostly agree, and where space feels like a stable stage. Near a black hole, the stage bends. Near an ultramassive black hole, the stage bends over distances so large that normal maps become misleading. A line on a diagram may represent hundreds of astronomical units. A region that looks close to the center may be larger than everything humans have ever traveled through. This is why comparing TON 618 to a planet is not enough. It is not a planet-sized object. It is not a star-sized object. It is not even a solar system-sized object in the ordinary sense. It is a gravitational region so large that the word object becomes uncomfortable. A black hole is often drawn as a ball, but the most meaningful part is not a material ball. It is a boundary around a region from which escape is impossible. The mass may be concentrated deeper inside according to the mathematics of general relativity, but the horizon tells the outside universe where the ending begins. And for TON 618, that ending is enormous. Now imagine the sky near it, not too close to be instantly destroyed by the quasar environment, but close enough for the black hole to dominate the view. The accretion disk might stretch across the sky as a distorted burning structure. Gravitational lensing would bend light around the black hole, producing warped images of the disk. The far side of the disk could be bent upward into view, making the black hole appear surrounded by a strange ring of light. Regions moving toward you could look brighter because of relativistic beaming. Regions moving away could look dimmer and redder. Light that barely escapes near the black hole could be twisted into paths that ordinary geometry cannot explain. You would not see a simple black circle in a flat orange ring. You would see a sky that has been rearranged by gravity. Behind the black hole, stars and gas could be magnified, duplicated, and distorted. Some light might loop around before reaching you. Some paths might be delayed. Some images might be from directions that no longer match ordinary expectation. The black hole would not merely block the view. It would make the view unreliable. This is another way TON 618 breaks reality for human minds. It makes seeing itself uncertain. On Earth, looking usually means trusting direction. If something is above the horizon, light traveled from that direction to your eye. Near a black hole, light can curve so strongly that apparent direction becomes a lie. You may see part of the accretion disk from the far side. You may see background light shifted around the horizon. You may see rings where there are no rings in ordinary space. Only paths permitted by curved space-time. The closer light passes to the black hole, the more extreme this becomes. There is a region sometimes described through the idea of a photon sphere, where light can orbit a black hole in unstable paths. For a non-rotating black hole, this is often discussed as a spherical region outside the event horizon. Real black holes likely spin, and the geometry becomes more complicated. But the central idea remains: gravity can bend light so severely that photons can circle before either escaping or falling in. For TON 618, even these light paths would exist on immense scales. A photon orbit is not a small ring around a tiny hole. It would be part of a gravitational structure larger than the familiar solar system. This is why the black hole shadow of an ultramassive black hole is such a strange concept. The shadow is not the event horizon itself, but a dark region on the sky caused by light paths that are captured or strongly bent near the black hole. In telescopes, black hole shadows are incredibly difficult to image, even for much closer objects like M87. TON 618 is far too distant and small in angular size for us to image its shadow directly with current instruments. We know it through its light, spectrum, and inferred mass, not through a photograph of the horizon. That gap between what we imagine and what we can see is important. Online, TON 618 often becomes a size comparison, a giant black circle placed beside planets, a dramatic graphic showing its event horizon swallowing the solar system. Those comparisons can be useful, but they can also hide the real science. TON 618 is not confirmed by a giant picture. It is not measured like a planet crossing a ruler. It is inferred from quasar physics. It is distant. Its host galaxy is outshone. Its central mass depends on models. Its exact numbers carry uncertainty. But uncertainty does not make it less impressive. It makes it more real. Real astronomy is often not clean. It is a careful reading of messy signals from places we cannot visit. And TON 618 is one of the messiest and most powerful signals we have. The next danger in the journey is the disk itself. If we imagine approaching the black hole not from the poles but near the plane of the accretion disk, the environment becomes almost impossible for matter to cross safely. The disk is not just hot. It is moving. It is dense compared with the surrounding space. It contains plasma, magnetic fields, turbulence, shocks, and radiation. A spacecraft entering it would not glide through like a boat through water. It would face high-energy particles and intense radiation long before contact with ordinary material became the main problem. The outer disk may extend across large distances. The inner disk may convert gravitational energy into light with extraordinary efficiency. As matter spirals inward, it can release a significant fraction of its rest mass energy before disappearing. That is why black hole accretion can be more efficient than nuclear fusion in terms of energy output per unit mass. The black hole does not burn fuel like a star. It allows gravity to do work on falling matter, and the surrounding material radiates the result. This makes quasars visible across cosmic distances. It also makes them hostile. A planet near a quasar would not receive gentle sunlight from one direction. It could be blasted by radiation from the active galactic nucleus. Chemistry in its atmosphere could be transformed. Surface conditions could become unstable. If the quasar produced powerful jets, regions along those axes could be especially dangerous. Jets can extend far beyond the central galaxy, carrying energy through intergalactic space. TON 618 is described as radio loud, which already tells us that energetic processes are producing strong radio emission. Radio loud quasars often involve jets. The exact geometry matters, but the larger point is clear. A quasar is not a quiet lamp. It is a central engine that can interact with its surroundings on enormous scales. If a jet from an active black hole were aimed near a vulnerable system, it could bathe that region in high-energy radiation. Even without a direct jet, quasar winds and radiation can influence gas far from the event horizon. Around TON 618, the environment would be shaped not only by gravity pulling in, but by energy pushing out. That push matters for the future of galaxies. Galaxies need cold gas to form stars. If a supermassive black hole heats or expels that gas, star formation can slow or stop in parts of the galaxy. This is called feedback. It is one of the key reasons black holes are important in galaxy evolution. They are not just passengers at galactic centers. They can regulate the growth of the galaxies around them. So TON 618 is not merely a monster hidden inside a galaxy. It may be part of the reason its galaxy evolves the way it does. That is a different kind of power. A black hole cannot reach across space like a hand. It cannot pull everything in from arbitrary distances. But through accretion, radiation, winds and jets, it can inject energy into its environment. It can change gas flows. It can help determine whether material falls into new stars or is heated and pushed away. It can influence structures much larger than the event horizon. This is where the scale becomes more subtle. The event horizon is huge. The luminous quasar region is larger. The affected gas can be larger still. The black hole is a compact gravitational ending, but the consequences are spread through space. Now step back again and think about the phrase, big enough to break reality. The reality it breaks first is the idea that size means visibility. TON 618 is enormous, yet from Earth it is a tiny point. The reality it breaks second is the idea that darkness means weakness. The black hole is dark, yet its feeding process can outshine galaxies. The reality it breaks third is the idea that ancient means simple. We see it in the distant universe, yet it is already unimaginably massive. And the reality it breaks fourth is the idea that objects are separate from their environment. TON 618 is not just a black hole. It is a black hole plus a feeding system, plus a galaxy core, plus radiation fields, plus cosmic history, plus the limits of our measurement. That is why the second half of this story can not only be about size, it has to be about consequence. If TON 618 were placed closer to us, it would not simply be a spectacular object in the sky. It would change the meaning of the sky. If it were inside the Milky Way at a dangerous distance, its quasar activity could threaten planetary atmospheres across huge regions. If it replaced the black hole at our galactic center, the structure of the Milky Way would be different. Stars near the center would orbit under a much greater mass. Gas would respond differently. The central region could become far more active if enough fuel were available. But it would not swallow the whole galaxy overnight. That is a common mistake. Even a very massive black hole does not magically vacuum up stars from across a galaxy. Gravity depends on distance. A star far away responds to the total mass inside its orbit, not to the drama of the word black hole. If the Sun were somehow replaced by a black hole of exactly one solar mass, Earth would keep orbiting almost as before, though it would lose sunlight and freeze. The danger of a black hole is not that gravity becomes infinite everywhere. The danger is that near the horizon, escape becomes impossible, and near active feeding regions, radiation can be devastating. TON 618 is terrifying not because it would instantly eat everything. It is terrifying because its scale rewrites what near means. For a stellar mass black hole, a few thousand kilometers can be close. For TON 618, even distances larger than the solar system can be part of the near environment. That difference matters for any imagination of travel. If you plotted a safe course around a normal star, you might think in planetary distances. Near TON 618, planetary distances are tiny. The event horizon alone can dwarf them. The disk and radiation zones can extend beyond them. A map of the region would need to use scales that make planets look like dust. There is also the question of gravity at the horizon. Counterintuitively, the surface gravity at the event horizon of a more massive black hole can be lower than that of a smaller black hole. This does not make TON 618 safe. It means the strength of the tidal difference across a human body at the horizon might be gentler than around a small black hole. A traveler could cross the horizon of an ultramassive black hole without immediate spaghettification at that boundary, at least in the simplified mathematical picture. But once inside, no engine can turn the journey around. The singularity, or whatever quantum gravity replaces it with, lies in the future of every inward path. This is one of the hardest ideas to explain without losing the calm thread of the story. Inside the event horizon, the problem is not simply that you need a faster rocket. The problem is that the geometry of space-time has changed the direction of possible futures. Escaping would be like trying to avoid tomorrow. It is not just difficult, it is outside the allowed paths described by general relativity. Even light, the fastest thing in the universe, cannot climb back out once inside. That finality becomes stranger when the horizon is gigantic. Crossing a boundary larger than a solar system and realizing that escape is no longer physically available is more unsettling than falling into a small hole. The scale gives the event horizon a quiet horror. There is no cliff edge. There is no impact. There is only a moment after which all roads point deeper. For an observer outside, the falling traveler fades. For the traveler, the outside universe may distort. The black hole's gravity can make the sky appear to shift. Light from the universe behind the traveler may be concentrated in strange ways. Depending on the path and rotation of the black hole, the view could become intensely distorted. In the final approach to the singularity, tidal forces eventually become enormous. Even around TON 618, the gentle horizon does not mean a gentle ending. It only delays the violence. This is a useful correction to another myth. Large black holes are not friendly black holes. They simply spread certain effects over larger distances. A person might survive crossing the horizon longer than they would around a small black hole, but survival is not escape. The horizon is a one-way border. After crossing, the question is not whether the traveler can go home. The question is how much time remains before the deeper structure destroys them. TON 618 turns that idea into a scale beyond normal stories. The event horizon is not the final object. It is the beginning of a region that the universe cannot report back from. No signal from inside reaches us. No photograph can show what happens there. No telescope can look past the boundary. Physics gives equations, but observation stops at the edge. That is another reason black holes remain so powerful in human imagination. They are not only dangerous, they are places where knowledge itself has a border. For TON 618, the border is vast. Now consider its lifetime. A black hole this massive does not evaporate quickly through Hawking radiation. For black holes of stellar or supermassive mass, Hawking radiation is incredibly faint compared with the cosmic background today. An ultramassive black hole would last for absurdly long times if left alone. Long after ordinary stars are gone, long after galaxies change beyond recognition, massive black holes may remain as some of the last structured objects in the universe. TON 618 is currently seen as a quasar, an active phase. But black holes do not stay bright forever unless they have fuel. Eventually, gas supplies change, mergers slow, accretion weakens. A quasar can fade into a quieter giant, leaving behind an enormous black hole that no longer announces itself with the same brilliance. The monster may become dark in a more literal sense, not because it is smaller, but because the surrounding fuel has diminished. That future is almost more frightening. A bright quasar is violent, but visible. A quiet, ultramassive black hole is an enormous absence. If it sits in the heart of a dead galaxy far in the future, surrounded by old stars and thin gas, it may no longer blaze across the universe. It may wait. Its gravitational influence remains. Its horizon remains. But the beacon fades. The universe has many ways of hiding its largest things. Distance hides them. Dust hides them. Brightness hides their surroundings. Time hides their origins. And eventually, darkness may hide their endings. The life story of TON 618 is therefore not only a story of size. It is a story of transformation. It may have begun from a seed in the early universe, grown through feeding and mergers, burned as a quasar, affected its galaxy, and eventually fade into a quiet remnant that lasts beyond almost everything familiar. That arc is what makes black holes feel less like objects and more like eras. A star has a life cycle. A galaxy has a history. An ultramassive black hole has both a local presence and a cosmic future. TON 618 belongs to the age of bright quasars, when massive galaxies and black holes were still growing through dramatic episodes. The light we see now is ancient evidence of that era. We are not watching TON 618 as it is today in the usual sense. We are receiving a message from its past, a message delayed by the expansion and age of the universe. The object may have changed greatly since that light began traveling. This is another layer of distance. Not only is TON 618 far away in space, it is far away in time. When we talk about it, we are talking about an event from the deep past that has only now reached our instruments. The quasar may be quieter now. Its host galaxy may have evolved. It may have merged with others. The black hole may have gained more mass or entered a dimmer stage. We do not know its present condition, because its present light is nowhere near us yet. So, TON 618 is not simply over there. It is then. The telescope turns distance into memory. That makes the object more haunting. We are not standing beside it. We are reading a fossil of extreme gravity. We are seeing a time when the universe had already built something so massive that our modern minds still struggle to place it on a scale. And because the light is old, every measurement depends on careful interpretation. Redshift tells us how much the universe has stretched the light. Spectral lines tell us about moving gas. Luminosity tells us about the engine's power. Models translate those signals into mass estimates. None of this is casual. Every number carries a history of assumptions. This should not weaken the story. It should make it stronger. A simple viral fact says, Ton 618 is the biggest black hole. A better story says, Ton 618 is a distant quasar whose light suggests an ultramassive black hole, one so enormous that even conservative estimates place it among the most extreme known objects, and whose exact nature is hidden behind distance, glare, and the limits of how we measure the universe. That sentence is less simple, but it is more real, and reality is more terrifying than the clean version. The clean version gives us a monster. The real version gives us a monster we have to infer from ancient light. Now imagine trying to build a physical model of TON 618 inside a human-scale room. If the event horizon were a sphere several meters wide, Earth would be microscopic. The Sun would be a speck. The orbit of Pluto might become part of a comparison line somewhere inside or near the dark region, depending on the scale chosen. The accretion disk would extend beyond the model. The broad line gas would be farther still. The host galaxy would not fit in the building, or the city, or the continent. Every scale model fails because the ratios become unbearable. That is not just a communication problem. It is a cognitive problem. Human brains evolved for landscapes, animals, weather, food, faces, and danger within walking distance. We can learn astronomy, but we do not naturally feel it. We use numbers as ladders. We climb them carefully, but at some point the ladder reaches a height where looking down no longer feels meaningful. Ton 618 sits at that height. It is not the only enormous black hole. It may not always hold every record, depending on how future measurements change. Other candidates exist. Some black holes may be larger. New surveys may revise rankings. But TON 618 remains culturally powerful because its scale is already far beyond common reference points. It became a symbol of the upper extreme, a name that people use when they want to imagine the largest darkness they can. That cultural role is useful if we treat it carefully. It can bring people into real black hole science, but it can also create myths. So we should say clearly, Ton 618 does not literally break physics. It does not prove that black holes can be infinite in mass. It does not swallow galaxies from across the universe. It is not a portal, and it is not a visible cosmic hole in the sky. It is a quasar powered by an ultramassive black hole, inferred from light and spectra, occupying a place in the distant universe where gravity, accretion, and cosmic history meet. That is enough. It does not need fantasy to be terrifying. One of the most concrete ways to understand its terror is to compare it with Sagittarius A, the black hole at the center of the Milky Way. Sagittarius A has a mass of about 4 million suns. That is already enormous by human standards. It shapes the orbits of stars near the galactic center. It has been imaged indirectly through the shadow produced by hot gas around it. It is not small in any ordinary sense, but TON 618 is thousands of times more massive. The difference between millions and tens of billions is not a small upgrade. It changes the horizon scale. It changes the timescales of motion near the black hole. It changes the potential luminosity of the accretion system. It changes what central engine can mean. If Sagittarius A is a hidden furnace in the center of our galaxy, TON 618 is a buried cosmic engine on a scale that makes our galactic center feel modest. That comparison also helps with another point. Our galaxy is not being torn apart by Sagittarius A because most stars are far from it. Black holes are not magical vacuum cleaners. The same is true at larger scale. Even TON 618 does not simply eat everything around it. It is the central engine of a quasar because gas is available and falling in, but much of the surrounding galaxy can still exist. Gravity organizes orbits. It does not automatically erase them. The real destructive power comes from the active phase: radiation, winds, jets, heating, feedback. These are less cinematic than swallowing, but more important for galaxies. A black hole that eats quietly is locally dangerous. A quasar can be galaxy-changing. Now let us return to the question of growth, because it is one of the deepest problems connected to objects like TON 618. Suppose the black hole began as a remnant of an early massive star. To reach tens of billions of solar masses, it would need a long history of feeding and mergers. But feeding is limited by the supply of gas and by radiation pressure. Mergers depend on the assembly of galaxies. Time in the early universe is limited. So astronomers study high redshift quasars because they are laboratories for black hole formation. Some models involve direct collapse black holes, where massive gas clouds in the early universe collapse into large seeds without first forming ordinary stars. Some models involve dense star clusters, runaway mergers, or repeated black hole collisions. Some require episodes of super Eddington accretion, where black holes grow faster than the simple Eddington picture would suggest for limited periods. The details remain active research. TON 618 may not be among the earliest quasars compared with record-holding high redshift objects, but its mass still makes the growth question severe. How does nature build something this large? How does it feed it? What galaxy surrounds it? What conditions made its central engine so powerful? These questions are not only about one quasar. They connect to the history of structure in the universe. Black holes and galaxies appear to grow together. The mass of a central black hole often correlates with properties of the host galaxy's bulge. That does not mean the relationship is simple or perfectly understood, especially at the extreme high-mass end. But it suggests that supermassive black holes are not isolated accidents. They are part of galaxy evolution. They grow inside cosmic environments that also build stars, merge galaxies, and channel gas inward. TON 618 represents that relationship pushed toward an extreme. A central black hole, so massive that it forces us to ask whether ordinary scaling relations still work. A quasar so bright that the host galaxy is difficult to separate from the glare. A distant object whose light carries clues about both gravity and galaxy formation. That is why its importance is not limited to size comparisons. It is a probe of how the universe builds its largest engines. The next layer is the surrounding gas. TON 618 has been associated with an enormous Lyman Alpha Nebula, a vast region of glowing hydrogen gas. Such structures can extend across hundreds of thousands of light-years around quasars. They are not simple halos, like an atmosphere around a planet. They are large, diffuse regions illuminated or energized by the quasar, shaped by gas flows, outflows, and the environment of the host galaxy. This makes the system even more physical. The quasar does not exist in an empty stage. It lights up material around it. It reveals gas that might otherwise remain invisible. It shows that enormous black holes are embedded in enormous reservoirs and structures. From a documentary point of view, this is the moment to widen the camera. We begin at the event horizon, then the accretion disk, then the broad-line gas, then the quasar winds, then the halo, then the host galaxy, then the cosmic web. TON 618 is a single name, but the full object is a layered environment. Each layer has a different scale. Each layer tells us something different. The horizon tells us about no return. The disk tells us about energy. The emission lines tell us about motion and mass. The halo tells us about gas around galaxies. The quasar's redshift tells us about cosmic time. And all of it arrives as light, stretched by the expansion of the universe into instruments on and around one small planet. That chain is part of the beauty of astronomy. But it is also part of its terror. We are very far from the thing we are trying to understand. There is no mission plan to TON 618. No probe can reach it. No human civilization could cross that distance in any practical sense with known technology. The object is so distant that even at light speed the travel time would be cosmological. And light speed is not a speed ships with mass can simply choose. For us, TON 618 is not a destination. It is an ancient message. That message says the universe can produce scales far outside human experience. And it says those scales are not decorative. They shape galaxies. They alter gas. They affect star formation. They survive into the far future. Now think about what would happen if a civilization lived in the host galaxy of TON 618 during its active phase. A world far from the core might see the quasar as a brilliant source in its sky, perhaps brighter than many stars, depending on distance and dust. Worlds too near the central region could be sterilized by radiation. Gas clouds might glow. Night skies might never be truly dark. The center of the galaxy could be both beautiful and hostile. If intelligent life existed in such a galaxy, it might develop under a sky influenced by an active nucleus. Their astronomy would be different. Their myths would be different. Their danger zones would be different. They might learn early that the center of their galaxy is not a calm place. Of course, this is speculation. We do not know if life exists in TON 618's host galaxy. We do not know the arrangement of planets there. But imagining the local sky helps us remember that quasars are not just points in catalogs. They are environments that could affect any worlds nearby. From Earth, the quasar is a distant dot. From inside its galaxy, it may have been a central cosmic weather system. The phrase cosmic weather may sound soft, but the processes are not. Radiation pressure, relativistic particles, shock fronts, hot plasma, and magnetic fields can shape space on scales beyond anything in a planetary atmosphere. A galaxy with an active quasar is not merely a collection of stars. It is a system with a central engine injecting energy into its surroundings. This is why black hole feedback appears in cosmology. Without feedback, models of galaxy formation can produce too many stars in massive galaxies. Energy from active galactic nuclei helps explain why some massive galaxies stop forming stars efficiently. It keeps gas hot or drives it out. It changes the future fuel supply. In that sense, black holes can help decide how galaxies age. TON 618 is an extreme example of a black hole, not as a passive grave, but as an active sculptor. The object destroys matter locally, but its larger influence is creative and regulatory in a strange way. By heating gas, it can prevent star formation. By launching winds, it can redistribute material. By glowing as a quasar, it reveals conditions in the distant universe. It is destructive, but it also helps write the history around it. That combination is unsettling. A black hole is not only an ending, it can be part of a galaxy's life cycle. Now, let us focus on the most dangerous misunderstanding of all: the singularity. People often imagine the singularity as a physical dot of infinite density sitting at the center. In classical general relativity, the equations point toward a singularity, a region where quantities become undefined, or infinite. But physicists do not generally treat that as the final, complete description of nature. It is more likely a sign that our current theory is incomplete at extreme conditions, and that quantum gravity is needed. So when we talk about the inside of TON 618, we should be careful. We do not truly know what happens at the deepest center. The event horizon is a robust prediction. The external gravitational effects are testable. The singularity is where our mathematics warns us that something deeper is missing. This is another way TON 618 breaks reality. It does not break the universe. It breaks our current description at the point where gravity becomes too extreme for known theories to remain complete. Black holes sit at the boundary between general relativity and quantum mechanics. They force questions about information, entropy, Hawking radiation, and the nature of space-time. TON 618, because of its scale, makes those questions feel enormous, even though the underlying physics applies to black holes of many sizes. The information paradox asks what happens to information that falls into a black hole. Quantum theory suggests information should not be destroyed. Classical black hole descriptions seem to hide it behind the event horizon. Hawking radiation complicates the story further. If a black hole evaporates over immense timescales, does the information come out somehow? Is it encoded in subtle correlations? Is our understanding of space-time incomplete? For TON 618, the evaporation time would be so absurdly long that the process is irrelevant to any normal cosmic era. But conceptually, the question remains. A black hole that could outlive stars, galaxies, and perhaps most ordinary structure still participates in the deepest puzzle in physics. This makes TON 618 both astrophysical and philosophical, but we should not turn that into empty poetry. The concrete point is this: the object forces known physics into regimes we cannot reproduce on Earth. We cannot build a black hole in a laboratory. We cannot simulate the full interior of an ultramassive black hole with certainty. We cannot observe past the horizon, so we use the universe as the experiment. TON 618 becomes part of that experiment. Its mass, luminosity, spectrum, and redshift are clues. Its existence tests our theories of growth. Its quasar phase tests our models of accretion. Its environment tests our understanding of feedback. Its horizon reminds us that observation has limits. Now, imagine the final camera move of this journey. We have traveled inward in imagination, from the distant dot to the galaxy, to the halo, to the disk, to the horizon, and then back outward into cosmic history. We have not solved TON 618. We have only learned how to ask better questions. What is the exact mass? How did it grow? What does its host galaxy look like beneath the glare? How much energy has it injected into its surroundings? Is its quasar phase temporary or part of a longer cycle? How many objects like it exist beyond the limits of current surveys? And what do they tell us about the largest black holes the universe can build? These are not small questions. They are not questions for a single telescope or a single paper. They belong to the long project of astronomy, where each generation reads the same sky with better instruments and finds that the universe was stranger than the previous generation could prove. Future observatories may refine TON 618's mass. They may separate more of its host galaxy from the quasar glare. They may detect structures around it with greater clarity. They may revise old estimates. They may find objects that make TON 618 seem less unique or confirm that it belongs to a rare extreme class. Either outcome is interesting. If TON 618 is rare, it tells us there are extraordinary pathways to building ultramassive black holes. If it is less rare than we thought, it tells us the universe builds such monsters more easily than expected. Neither answer is comfortable. One makes TON 618 a cosmic exception. The other makes it part of a hidden population, and hidden populations are often how astronomy changes. For a long time, quasars themselves were mysteries. They looked like stars, but had strange spectra and enormous redshifts. Only later did their nature become clearer: active galactic nuclei powered by supermassive black holes. What once looked like a point of light became a galaxy-scale engine. TON 618 belongs to that tradition. It reminds us that a dot can contain an entire violent structure. The object is not terrifying because it is close. It is terrifying because distance does not make it small. It is not terrifying because it will harm Earth. It is terrifying because it shows what the universe can do without needing to harm us. A storm does not have to reach your house to prove it is powerful. TON 618 is like that on cosmic scales. It is a storm of gravity and light, so far away that the danger is not personal, but existential. It changes how large the universe feels. It changes how young the early universe seems. It changes how confident we can be in simple explanations. And maybe that is the real ending of this story. TON 618 is not only a black hole that is big enough to break our sense of scale, it is a reminder that the universe is not built around human categories. The categories are ours: star, galaxy, black hole, object, distance, past, present. We place these words over reality to make it readable. Most of the time, they work well enough. But then, something like TON 618 appears, and the words begin to strain. It is an object, but also an engine. It is dark, but also the source of a quasar's light. It is ancient, but visible now. It is distant, but it informs our physics. It is a boundary, but also a question. That is why the calmest way to think about it may be the most unsettling. Do not imagine TON 618 as a monster chasing anything. Imagine it as a fact that exists whether or not the human mind is comfortable with it. A fact measured through ancient photons. A fact large enough that the solar system becomes a poor unit of comparison. A fact bright enough that its own galaxy hides beneath its glare. A fact dark enough that no signal can escape from its central boundary. And a fact uncertain enough that science must keep refining it. There is no need to exaggerate beyond that. The universe already did. If TON 618 were small enough to understand easily, it would not matter. In the same way, if it were close enough to see clearly, it might be a danger rather than a mystery. If it were quiet, it might disappear into catalogues. But it sits in the strange middle, unimaginably large, violently bright, deeply distant, and still hidden behind the very light that reveals it. That is the shape of the terror. Not a jump scare, not an impact, not a sudden ending. A scale so large that it makes the mind slow down. A light so old that it turns observation into time travel. A darkness so wide that crossing its boundary would be a journey into a future with no outward path. And a growth history so extreme that it asks whether the early universe was capable of building cosmic engines faster and larger than our simplest expectations allow. TON 618 does not break reality. It breaks the version of reality that feels comfortable. It breaks the idea that black holes are small dark pits. It breaks the idea that distance protects our imagination from scale. It breaks the idea that the early universe was too young to contain enormous structures. It breaks the idea that darkness and brightness are opposites, because here, the brightest signal comes from the edge of the darkest place. That is the final paradox. The black hole cannot shine, but the quasar around it can be one of the brightest things in the universe. The event horizon cannot send information out, but the gas dying outside it can send light across billions of years. The center is hidden, but the surrounding violence reveals that something enormous must be there. And we, sitting on a small planet around an ordinary star, can receive that message. We can split its light, we can measure its lines, we can estimate its mass, we can argue over the numbers, we can improve the models. And still, after all of that, the object remains larger than the feeling of understanding. That may be the honest place to end. Not with certainty pretending to be complete, but with a clearer kind of awe. TON 618 is not terrifying because it is supernatural. It is terrifying because it is natural. Because the same universe that made oceans, clouds, trees, and human eyes also made an ultramassive black hole, whose event horizon could dwarf the solar system, whose quasar light can cross most of cosmic history, and whose existence forces us to rethink how large, bright, ancient, and hidden a single thing can be. That is why TON 618 feels big enough to break reality. Not because our ordinary sense of reality was never large enough to hold it,